Okay, so let's look at the general structure of a Geant4 simulation. So we're in our home directory. Let's go to our simulation folder, edepsim. So now that we're in our project directory, so we can see our .cc file or our main. So our edepsim.cc, and we've got our source and our include. So if we were to list contents of our source files, we've got these 1, 2, 3, 4, 5, 6, 7, 8 classes, and let's just open our main. So our main file, so in this case, our main file, and you can tell if it's main with this int main, but our main file will be located in the project directory. So in this case, it's the edepsim directory. And what this does is it manages how all these classes or files work with one another, and in the more general sense with the Geant4 source directory, which it's located in a separate directory where all these pre-compiled headers, like all these G4 files, located. But just talking about the main itself, or the edepsim.cc file in particular. So what this file does is it manages how these classes work with one another to produce the ending result. So in Geant4, there's 3 compulsory classes that the user has to define, and this is the detector construction, the primary generator action, and the physics list. So as you could probably tell from these names, the detector construction, what it does is it defines the geometry of the world, and the reason why it's called detector construction instead of, say, something like geometry construction or world construction or something like that, it's just due to the historical reasons. Geant4 was conceived for high energy physics, and in high energy physics, what you're simulating is just these big detectors. So all their simulations revolve around detectors. So the geometry file or class is called detector construction. And what the physics list does is, as you can probably guess also, is it manages the physics in the simulation. So you tell it what particles to create and what processes to govern will exist for those particles. So you might be thinking, well, why don't we just include all the physics possible in every simulation? Well, Geant4 is used for a wide range of things. It's used all the way down to like the molecular level using the Geant4 DNA physics, which models how cells do damage. They've got chemistry, and this goes all the way down to a few EV. So they go down to tiny interactions. Whereas on the other side of the scale, where it's made for high energy physics, we go up to TeV. So a factor of 10 to the 12 difference between these two applications. So if you're doing high energy physics, you don't care anything about all these low energy interactions that you would care if you're looking at damage to DNA or something like that. And if you're looking at damage to DNA, you don't care about all these exotic particles that are generated at high energies. So that's why there's this physics list where you tell the simulation what particles you want to include and what processes. You don't include everything because that would just take forever to run when you don't need it to take everything, because there'd be no difference if you include these certain processes or not. And the final the class that a user has to include into a Geant4 simulation is the primary generator action. So I'll actually just open up the primary generator action now. And if you scroll down, all this stuff is commented out, but all that's actually being done is the GPS gun. So in Geant4, you can either use a general particle source or you can use a particle gun. So a particle gun is when you actually write code within the program itself, whereas the GPS gun or the general particle source is just macros which you can change particle interactively outside of the compiled simulation. So if I were to open one of these .mac files, so let's just go run neutron.mac, then we can see all these options for the beam or the particle being fired, and we define the particle here where it starts, so the center, its direction, so in this case it's the beam's going the minus z direction, and it starts at 0, 0, 0. So just the origin of the world describes what the beam is. So those are the three main classes. So the detector construction, it creates the world where our particles will be transported in, and then we have our physics list, which describes the interactions which the particles will that the particles will be interacting with the matter in, and all the processes that undergo there. And the primary generator is just to describe the primary particle which is fired, which is, for our case, we'll be using the general particle source, so we can just change the particle outside the simulation itself and just use macro files. So if we want to change the beam, we don't have to compile. But if we actually were to look into our main file, our edep.sim.cc, so remember this file, it tells the simulation how all the other classes work together. So, and this is done with the G4 run manager, and so you can see here on this line, creates a run manager, and then with that, it does all the communication, like it creates all these separate classes. So in this case, we have an analysis manager, and as you would guess, does analysis like stuff. So in our case, this creates stores quantities in files and saves it as an output file, and it also initializes it. So in this case, initializes the different classes. So for this case, we've got our physics list, so what describes all the particles and processes. And if we wanted to, if you actually look, there's a dedicated physics list.cc, but if we wanted to, we could just have a single command in our main file, and we could just use an existing physics list, which is as a recommended physics list, which has already been written. But in our case, we just use our physics list that we've chosen to do what we're interested in. So, and then you see it initialize the detector component, so the geometry of the world, and then you also see this action initialization thing being initialized here. So when we listed our contents in our source file, so we saw this action initialization class, and what this does is it just executes all the the non-compulsory classes. So in this case, and for some reason we've got the primary generator action, but that's just a bit of a error. So this should actually be in the main with all the other. And when I say it should be, this is just the Geant4 recommended technique. So the recommended technique is to have all your compulsory classes in the main file, and then to have all your and remember, all the compulsory files are your detect instruction, your primary generator action, and your physics list, and they describe all the minimum components of a simulation needed to run. So, and then outside of that, the recommended coding technique is to have an action initialization class, and then that handles all the non-compulsory classes. So in this case, we've got a run action class, and all this pretty much does is gets the simulation to start running and stops the simulation. Like when we run it and you see, shooting X amount of particles and finishing up, that's, mostly what we see the run action do for our simulation. And then we've got this steppy action class. So we'll look a bit later into this, but this just deals with particles interactions as they traverse the world, and that's the main parts of the action initialization. So just to give an overview, Geant4, as they say, best practice is to have your compulsory classes in the main. So in this case, we should have had the detect construction to describe the geometry that particles will be traveling in, and our physics list to describe the particles and processes which will be having in our geometry, and then a primary generation which we will naughty and put in the action initialization class, which will actually show a particle. And then we have this user class. Bit of a tongue tie. We have this class called the action initialization, and this class manages non-compulsory classes that we've defined in our program. And remember, a class is just a collection of functions and codes to perform a particular end result. So the detect construction class, it's just got all this code to define a geometry which we use. The primary generator just has all this code to define how we shoot a particle, its distributions, its energy, and stuff like that. And after we have this action initialization, then you'll come down to this visualization comment here. So here you'll see if argument count equals 1, then do this command here, generate a UI, and if the argument count isn't equal to 1, then don't create this. And then if we go down, you'll see if UI does not exist. So if argument count wasn't equal to 1, then this wouldn't occur, and in which case this would happen instead. So you might be thinking, what's the argument count? So if I go into the build directory and ls for fun, and if I go to run the simulation, so, and if I want to add a macro to it, like so, then every time you run a program, then all these additional arguments that you give after the program name, so edepsim, they're additional arguments, and they can be passed into the main. So if we open our main, go to the top, you see that this main, so sorry, I should point out just in case you haven't got a background function. So this int on the left, this is what the function will return. So in this case, it's saying we've got a function called main, and it will return an integer once it's finished running. So in this case, we've got to return 0. So that's an integer, so a whole number. And that's what this function will return once it's finished running. And then inside of these parentheses of the function, so these are the inputs that are going into this function and then outputting our output, in which case it's just a return 0. So just a bit of background. It's traditional to, when you have a main, you have a return 0, and then you can check the return status of a program. And if it was 0, it means it was run successfully. And if it was a non-zero value, then it means something went wrong. So back to these input functions, we've got two inputs. We've got an integer of argument counts, and then we've got a character, well, technically it's an array of characters or strings or text, if you prefer, of these values, argument values. So when I'm running this program, I've got these argument values here. So run electron.mac, it's an argument value, and it's, if I added another, let's say run.mac, I would have a second argument value in addition to this run electron.mac. So I could just keep giving more argument values. I could even say have like 12.7 if I set up my program to take in saying like energy or position of some detector or phantom in the world. So, but if I run with this edepsim, then this is counting as one argument in total. So this is stored as so when we run this program, it stores all these separate arguments separated by a space into an array or a list, if you prefer, of arguments we're inputting. So our first argument is just edepsim, and that would mean we've got one argument value. So it gets a bit iffy in C++ because when we store quantities into a list or an array, like a matrix, so when we're storing all these quantities into a collection, then this first argument is given an address of 0. So if you play with matrices, and if you've got like a 2x2 array, you might reference it as 1 2 1 2, or it might be 0 1 0 1. So even the first entry might be 0, or you might be used to giving it a value of 1. But in the case of C++, our first entry into the matrix or the array is given a 0 value. So but the argument count, which representing the size of this matrix or array, is still 1. So if we were just to enter just the program by itself, we would have an argument count of 1, and argument count, the first entry of the argument count would be in this argument value array, and that would be referenced as argument value 0. So sorry about this bit of confusing like terminology if you're new to C++ and how quantities are stored in arrays, but just be aware that when you see this, if you argument count, it's just referring to how many things were entered with the program itself. So we could have, so in this case, we would have an argument count of equal to 2, and then we would have this argument value array, and so argument value 0 would be edepsim, and argument value 1 would be this run electron.mac. So in total, we would have 2 arguments, and though they're referenced in a slightly in an n-1 fashion. So the first one is 0, the next is 1. So with all that roundabout explanation and blabbering, we come to how the program knows to whether to run visually. So if we just run edepsim like this, and we wait for it, and we pop up with our visualization, and we can rotate all that. And if we wanted, we could give it commands interactively, such as run beam on 10, and we could run that and do various changes of the angle if we wanted to specify a specific angle that we want to look at it. But if we just run it instead with one of the macros, then the main won't do the commands to set up the visualization. In this case, it's this UI executive. So if we have more than one argument, so if we run additional things besides just the program name, and then the main will not set up the visualization. And in that case, we're running what we call batch mode. It's called batch because we're just running it for speed, because if we ran in visualization mode, it would be very slow. We'll be looking at all the particle tracks in the world, and we'll just be wasting processing power to look at it. But if we just want the end result of some particle going through the world, like the energy it deposits in some volume, then we don't care about the visualization, and we just want to run all the commands in the macro itself. So sorry for going a bit off the rail. We're talking about this argument count and argument value in terms of how it's defined when you're running a simulation, whether it's in batch mode, so when you give it an additional argument after the program name, or whether you just run it by itself in interactive mode. But just as a quick recap, so when we go into our project file, so let's go back up from the build. Then we've got our main file, our .cc file, like for just in any general program, and then our .cc or our main file. What it will do is it will manage all the classes, and all these classes we can find in our source and our include directories, and they'll do specific things for it in our simulation. And in Geant4, we've got 3 compulsory classes that we need to describe. So the detect construction, which describes our geometry, and so in all of the materials, so the geometry that particles will be interacting in. And then the next compulsory class is our physics list, which describes what particles we want in our simulation. and what processes that we're interested in. And then finally, we have the primary generator action to fire our the particle that we're interested in creating, and then that particle gets tracked in our geometry, which is created by the detector construction, and then the physics list manages all the interactions and any secondary particles which will be created when it interacts in the detector geometry. And if we want to add additional classes to describe other things, so if we wanted to like score certain quantities, then we might want to make a sensitive detector class, or in our case, we've got a stepping action class. And if we were following best practice for Geant4, we would have an action initialization class, and that would then create all the classes to be used for the simulation. And so that's the the main parts of our simulation. So in our case, we never really want to, well, we won't ever really need to touch our main file, because it just manages how the classes work together, and we won't really be changing how the classes actually work with one another. We'll be just changing the specifics themselves. So in our case, we'll just really be editing the files, the class files themselves, such as detector construction and stepping action, and things like that. And the Geant4 simulation, or the main, determines whether to run in interactive modes or visualization mode, when we're actually see the world itself, or whether it will just run in batch mode. So when we've giving it macros to run based on how many arguments we pass to the main. So, and that's just, the main gist of our simulation, or our project file, our project that we'll be working with.